Okay, so the plan for today is to discuss the construction of this Floer homology, and I would like to start by giving some background. So, very briefly, I'd like to talk about Lagrangian Floer homology. Since the construction that we're going to use will heavily depend on techniques coming from symplectic geometry, I'd like to talk a little bit about them. So here the background is that we have symplectic manifold. With the symplectic form omega. So here symplectic means that it's closed and it's non-degenerate. Meaning that if x is non-zero, then there is a y such that omega xy is non-zero. So omega is a 2 form with these properties. Then that symplectic form, the manifold with the symplectic form is called a symplectic manifold. And what we need for the Lagrangian Floer homology is inside that symplectic manifold we need two subspaces, L0 and L1, that are half-dimensional, and they are Lagrangian, meaning that the symplectic form vanishes. So if we are in this case, then we have a symplectic manifold and two Lagrangians that are intersecting transversely, and some mild topological conditions about the fundamental group of M and L0 and L1 and the second homotopy groups. So in some cases, one can define a homology theory corresponding to this pair, and this is generated by the intersection point and the boundary map. And since it's generated by the intersection point, then it's enough to define the boundary map on the generator. So the of course formally it will look like I guess the sum of other intersection points, and here you take some numbers times y, then these numbers cxy correspond to counting holomorphic disks. Between x and y. So what does that mean? In order to really set this up, we need to talk about a holomorphic structure on M. In fact, we're going to talk about first we need an almost complex structure. So that would be a map from the tangent space to itself with that its square is minus the identity. So and it also has to be an almost complex structure that has something to do with the symplectic structure, so we require and also need the condition that yes, omega x j of x is greater than 0 for x non-equal to 0. In other words, when we have an almost complex structure, this multiplication by j is something like multiplication with I. Like if we would have an actual complex structure on the manifold, then multiplication by I would be such a map in the tangent space. And what this condition says that the symplectic structure on complex lines is positive. So that's sort of a meaningful condition. So if we have, so we start with a symplectic manifold with and these Lagrangians. We fix an almost complex structure that satisfies this condition, and then it makes sense to talk about almost, I guess, complex, makes sense to talk about J-holomorphic disks. So this is not really holomorphic, but J-holomorphic. So fixing such a J, we can say that a map U from the disk to the manifold is J-holomorphic. Then we think of the disk as the unit disk, and here we have M, right? And what we want is that D of U is compatible with the almost complex structure on the disk and this almost complex structure M. In other words, it commutes with multiplication with I here and multiplication with J there. I here and J there. So that's a J-holomorphic disk. And when I say counting J-holomorphic disk between X and Y, I will be looking at maps U from the unit disk to that sort of interpolate between X and Y. So more precisely, this disk, so this is minus I, this is I. Let me call this arc here E0 and this arc to E1. And what our condition is that U is J-holomorphic. I guess that's the first condition. And the second is that U of E0, the boundary maps to L0. This other side of the boundary maps to L1, and minus I is mapped to X, and I is mapped to Y. So at least now, after we fix such a J, it makes sense to talk about holomorphic disks. Sometimes it's called holomorphic strips connecting X to Y. What do I mean by counting them? Now, one has to be a little bit careful, because this could be in general, even after you fix x and y, it could be that the moduli space of such holomorphic disk is not zero dimensional, and it's sort of hard to count it. So first of all, there is an R action on the moduli space. Right? So okay, mxy is u as before. So U is a J-holomorphic disk connecting X to Y, and the collection of such maps you can put into a moduli space. Okay. And I claim that there is an action of R on this moduli space. What is this action? Well, the observation is that if you take this holomorphic disk, you take this holomorphic disk U, then it is possible to reparameterize this map in the following way. So take the unit disk and note that that there are some automorphisms of the unit disk that keep minus I and I fixed. One beautiful way to see that is by using the Riemann mapping theorem. You can imagine that this holomorphic, that this unit disk, think of this unit disk as an infinite strip. Okay? So then minus I is in this way and I is that way. And then clearly the translation will be a holomorphic map that will fix the boundary. The boundary maps the boundary, and I maps to I, and minus I maps to minus I. So, and this is clearly a one-parameter family of reparameterizations. Is that okay? Of maps from, I guess, D2 to D2 that keep I and minus I fixed. Now, and of course, if U is J-holomorphic, then after I reparameterize this map by precomposing with this self-automorphism of the disk, then I would get another J-holomorphic disk. Is that okay? Great. So, and that is the R action on M. And at the end, we don't really want to distinguish between holomorphic disks that are basically the same, except that they are just reparameterizations of each other. So we usually will look at this space M hat xy, which is M xy, divided by the R action. That's the first remark. The second is that if you fix the homotopy class of this disk, just look at, instead of J-holomorphic disks, look at just topological disks that satisfy these conditions, that the left side of that disk maps to L0 and the right side maps to L1, and the two endpoints map to X and Y. So if you just look at topological disks, maybe let's call that space P2 xy. So equivalence classes of topological disk connecting X to Y. Then there is a map which is called the Maslov index. that satisfy some nice properties. I guess it's additive, so if I have a disk phi1 connecting x to y, and I have a disk connecting y to w, maybe call this phi1 and phi2, then the Maslov index of phi1 glued together to phi2, if I glue these two disks together, then I will get a disk that maps to, right, composing with this map, I will get a disk that this point maps to x, this point maps to w, and the left side maps to L0 and the right side maps to L1. So this is an element in pi2 xw. This is not the best notation, but okay. Then this is m v1 plus m v2. And I guess the other property of the Maslov index is that m of phi is the formal dimension of the moduli space. So previously we had this mxy, which is the moduli space of all J-holomorphic disks connecting x to y. Now sometimes pi2xy is empty, and in that case that there are no topological maps, so there are no holomorphic maps either. But sometimes pi2 is really large, and in that case you could have different components of these topological maps. The Maslov index is well defined if you fix one homotopy class, so I guess m of phi union of phi in pi2xy is the thing that we have defined mxy before. Okay. So if you take m of phi, then that has an expected dimension, the formal dimension, and if the original symplectic manifold is reasonable, you know, something like the first Chern class evaluated in a sphere, so in reasonable cases you can prove that for J generic m phi is a manifold of dimension. Do I have too many m's? Yes. Right, so I know it's bad, so curly m will be the moduli space, and if I can still make changes, like little m be the Maslov index. So then this moduli space has dimension m of phi. And sorry, I would like to just clarify what that means. So there are homotopy classes for which the Maslow index is negative. And of course that doesn't mean that then the corresponding moduli space is a negative dimensional manifold. So what I really mean here, or more precisely, M phi is either empty or a manifold with dimension equal to M of phi. So in particular, if M of phi is negative, then the moduli space has to be empty for generic J. And this doesn't hold in general, so you really have to assume something about the symplectic manifold in which you work. But maybe more on that later. So, so let's go back to this CXY. So that is really is going to be a sum for homotopy classes in pi 2xi that satisfy that the Maslow index is equal to 1. And then I count the number of elements in the moduli space of phi divided by R. So okay.
So is that if Maslow index is less than or equal to 0? I mean, because you always have to be, if there's anything in it, it's at least 1.
Well, this is true, right?
Yeah.
If you want to add something to that, if M of phi is 0, then either x equal to I and phi is trivial, and in that case the moduli space of phi is just one point, the constant map, or M of phi is that better? Okay, so in general, if the moduli space is 0, if the Maslow index is 0, then, well, I guess you know it has to be a 0-dimensional manifold, which could still be finitely many points. However, we also have this R action. And you can see that if the map was not constant, then when you are looking at different elements in that R action, you should get a one-parameter family of moduli spaces, so that somehow contradicts the fact that it's 0-dimensional. So the interesting case really happens when the Maslow index is 1. So in that case, this is one-dimensional. However, we can mod out by this R action. And with some work, we can also prove that it's a compact 0-dimensional manifold. So there is hidden here, there is also the statement that M of phi divided by R is compact. If not, then we cannot really count the number of points, and then we count the number of points either with mod 2, which is great, or we have to worry about how to orient this moduli space, which is in most cases possible. Depends again on the manifold M and on the two Lagrangian subspaces. So there is also an issue about orientation. If you don't like orientation, just count mod 2. But most of the cases you can make this count in Z, and then you have this well-defined element, and this is the boundary map. And with some work, usually can prove that d squared is 0, and then I guess this homology of L0, L1 is the homology of this complex. So, in a nutshell, that's Lagrangian Floer homology. And this is not something that works for every symplectic manifold and every pair of Lagrangians. Floer defined it in the simplest case, and then there are lots of work. There was lots of work done to extend that. But this is the general setup, and we are going to use it in a very special case, in which case, luckily, everything works, so it's possible to do. Okay. So we want to apply this general theory in a special case. In the following case. So I should like to mention in general, this is some kind of invariant of two Lagrangian subspaces in a symplectic manifold. What we really want, on the other hand, is a three-manifold invariant. So somehow we have to set up this construction in such a way that it corresponds to a three-manifold. So we have to start, that would be a long story, we have to start with three manifolds and what kind of information we can associate to a three manifold, and eventually we are going to get these large space and these two subspaces. Okay? So we have a three manifold Y is oriented closed. So it's compact, has no boundary, and we also will assume it's connected. And we will use Heegaard diagrams so that will be the topological input that we need, and then eventually we can run this symplectic geometrical argument. So what is a Heegaard diagram? We'll need an oriented surface with genus G, and inside we will need some simply closed curves, G of them, and another set of simply closed curves, again G of them. And we'll all, well, let's move. So alpha I are simple closed curves, circles, and the same is true for beta I. And we need some extra conditions, and these are that the alpha circles are disjoint from each other. The beta circles will be also disjoint from each other. The alpha and the beta circles could readily intersect. In fact, those correspond to our generators. But we need an extra condition about that these circles are linearly independent in the first homology also. That. also. Linearly independent. There could be relations between the alpha and the beta circles, a homological relation. We don't exclude that. Okay, so one example, G is equal to 1. This is alpha and this is beta. One other example, again G equal to 1. This is alpha and this is beta. And soon we will have lots of other much more interesting examples. Okay? Some examples. Okay, I claim that once we have a Heegaard diagram, we can associate to it uniquely a three-manifold. Okay, so and in fact that's quite easy to do. So let me try to draw a picture. So first, you take sigma g cross an interval, at least now that's three-dimensional, but not yet a closed manifold. And now we are going to use the beta circles. So what I'm going to do for each of the beta circles, we are going to add something to this three-manifold. Okay? And the picture is, say this is beta 1. Then for that, I'm going to add a three-dimensional region like this. And this is really adding a D2 cross an interval. So note that the neighborhood of beta is an interval cross S1, right? This is the interval, and this is the S1. And we use this annulus to attach this D2 cross an interval. Yeah, should have written I cross D2. Is that okay? And I will do this for every beta circle, okay? So after I've done this, right, added some stuff like that, I will get some kind of manifold, right, n of beta. Note that this operation of attaching these disks or discus intervals to our manifold changes the boundary, changes this upper part of the boundary, right? We remove from the boundary the neighborhood of beta, right, because we attach something to that, but we replace that boundary with something else. So we cut out an S1 cross an interval and we replace it with two disks. And that changes the Euler characteristic of the boundary. It adds Euler characteristic 2 to the boundary. So originally we had the Euler characteristic was 2 minus 2g. We do this g times, so we get a manifold, a two-dimensional manifold with Euler characteristic 2. And I claim that that other boundary has to be a two-sphere. Okay? It has, and why is that? Well, all I have to prove that whatever I left with at the end is connected. So So maybe call this T of beta, this boundary, and claim T of beta is a two-sphere. Well, first thing we have seen that the Euler characteristic of it is equal to 2. We need to prove it's connected. Otherwise, it could be a torus and a sphere, for example, right? So I guess for that, there is this small exercise to work out, which is that T of beta is connected if and only if sigma minus beta 1 minus beta g is connected, which is true if and only if beta 1 beta g is linearly independent in H1 of sigma g. So that's an easy exercise, and we already assumed in the definition of a Heegaard diagram that this holds, so this holds, so this is connected, so at the end you get a sphere. Is that okay? So great. So after we have done this, we used up already all the beta circles, and we ended up with something plus an extra boundary, which is S2. Now let me add just a three-dimensional disk up there, and then that will be at least a manifold that doesn't have any boundary in this direction, right? We still have this boundary, this sigma g, but don't forget that we still have these alpha circles, right? So we have only done half of the thing, so now I'm going to look to this manifold from the opposite direction, and from this way I will also attach these disks cross intervals, right? After I've done that, I get this manifold. Again, the alphas are linearly independent, so I have to get a sphere. So here's S2, and now I'm going to finish it, and then lo and behold, I get this closed three-manifold. It's easy to see it's oriented and connected. Okay? So this is a very elementary construction that associates to a Heegaard diagram a three-manifold. Let's investigate a little bit this. So in fact, we got a little bit more than just the three-manifold. We got two pieces in that three-manifold that are, I'm going to call U beta, the one that corresponds to beta, and U alpha, the one that corresponds to alpha. And if you want to fix orientations, sigma is oriented, so you just have to say how the three-manifold Y is oriented. I can say that, well, I orient U alpha in such a way that the boundary of U alpha is sigma g with the right orientation. That orients U alpha. Similarly, you orient U beta in such a way that boundary of U beta is minus sigma g, and then you have the orientation of Y. Okay? So what is topologically U alpha and U beta? Well, it's not hard to see if you don't see it, just try to work it out at home. That this is a handle body. of genus G. And one way to see what the handle-body is, just draw this surface the same way as I did in R3 and take the inside, and that's a solid three-dimensional handle-body. Okay? Or if you don't like this picture too much, just take a ball and to that ball attach arcs and then make them solid, right? And that's also, if you do this G times, that's also a G-dimensional handle-body. And it's easy to see that when you do this operation, you always have to get a handle-body. One way to see that is, well, in general, you have these alpha 1 to alpha G circles, but there is a diffeomorphism from sigma, from that sigma to this sigma, that maps the alpha circles to these standard circles. And then, well, let's see what happens if I follow this construction. I have to attach, in this picture, I have to attach these disks along these circles, right? So, for example, this will be a small neighborhood of that circle, and when I attach it, I could really do it in the picture, and I get this region right here. Is that okay? I do this here, and here, and here, and then I get this three-manifold that has a boundary. The boundary is a sphere, and you can see the boundary of that sphere is really this region, right? And so you can also attach this large disk, D3, which is whatever is left out, and you see in this way I exactly build up this handle-body. Is that okay? Or if you really like this picture better, then think of that will be, right, my filling. And I really get a ball at the end. Okay, so what we really have is a decomposition of Y into two parts, U alpha and U beta, along their common boundary. So this is a handle-body of genus G, this is a handle-body of genus G, and this is the common boundary, right? Such a decomposition is called a Heegaard decomposition. Is that okay? So what we have seen is that our Heegaard diagram always gives us a Heegaard decomposition. In the Heegaard decomposition, we forget the position of the alpha and beta circles. We just remember the handle-body that we built up. And surprisingly, this seems a rather elementary construction. It's true that every three-manifold can be decomposed this way. Y is oriented, closed three-manifold, then Y admits Heegaard decomposition and also a Heegaard diagram. By the way, if we have a Heegaard decomposition, then we always can find a Heegaard diagram. Why is that? Because what is the decomposition? We just have these solid handle-bodies glued together along the common boundary, right? So this is my handle-body right here. I call it U alpha. Now in order to have a Heegaard diagram, all I have to do is to find some alpha circles, right? So for example, I can choose these alpha circles, and we already seen that that builds up that handle-body, right? Unfortunately, this is not unique. So the Heegaard decomposition contains less information than a Heegaard diagram. And this is because in this picture, I have various choices. I could use this as alpha to alpha 3, alpha 4, and alpha 1. And this will correspond to this solid handle body inside of this surface, right? But I could also choose these sets of circles, right? And it's easy to see that you again build up the same handle body. So, and just something to keep in mind. Okay, so we have this theorem, and well, there are lots of ways to prove it. But maybe next time I will talk about the more theoretical proof. But one way to see that is to start with a triangulation. First you have to prove that such a three-manifold admits a triangulation, but after you have done this, right, you have these tetrahedrons inside your three-manifold, and you just take these points and the edges between them and enlarge them somewhat. Okay. And what you would like to see that, first of all, the neighborhood of the 1 cells and the 0 cells is a handle body. Just sort of see it in this picture, right? It's going to be a collection of balls added together. And that the complement is also a handle body. Now, in order to see the complement, you have to realize that for such a triangulation, you have a dual triangulation, which is that you replace the triangles with the center, and you replace the tetrahedron with its center, and whatever is left is going to be a small neighborhood or some neighborhood of the dual. So, so that's a handle body as well. So the three-manifold can be decomposed into two handle bodies joined along the common boundary. That's a Heegaard decomposition. Proof is neighborhood of 0 cells and 1 cells, and U beta is the rest. So at first sight this seems rather surprising, because you know that three-manifolds are rather complicated. On the other hand, you also see that every three-manifold can be described in just by very elementary pieces, taking two solid surfaces like that and then gluing their boundary together. And the point is that there are lots of different ways to glue these surfaces together, and it turns out that, well, it's sort of hard to classify three-manifolds using this technique. Okay. Great. So what we learned so far is that if we want to study three-manifolds, it is okay just to study Heegaard diagrams, because given a Heegaard diagram, I can just uniquely write down a three-manifold. But if I have a three-manifold, not uniquely, but eventually I can find lots of different Heegaard diagrams representing that three-manifold. Now what we'd like to do is to define a three-manifold invariant that uses one Heegaard diagram. Okay? And, well, in order to prove that the three-manifold invariant, we have to prove that no matter what Heegaard diagram we choose, for the same three-manifold, we always will get the same invariant. Okay? But we have to start somewhere. So right now we are going to fix a Heegaard diagram. For y. And then I just have to tell you in what setup I would like to use this Lagrangian Floer homology. So first I need an ambient space that used to be called M. So now that will be replaced by something that's called the symmetric product of sigma. Sigma is a surface of genus G, and I'm using the G-fold symmetric product. These are the same numbers. So basically they're just taking G copies of sigma and then divide the symmetric group on G letters. Okay? In other words, the symmetric product is taking G tuples of points, maybe the unordered G tuples of points. I could choose the same point G times, or I could use this point 2 times and some other point, well, you know. So in other words, there is this action on the symmetric group on G letters on this space, and it doesn't act without fixed points. The fixed points will be the multiple entries, but surprisingly this is really a manifold. Okay? So this is actually a manifold. In fact, fixing a complex structure on sigma G induces a complex structure on M. Also have a Keeler structure, so also a symplectic manifold. And instead of L0 and L1, we'll use, we'll call this T alpha, and this will be the product of the alpha circles. And this will be T beta, which is the product of the beta circles. So what I mean that a typical element in T alpha will be a collection of G points, and one point will lie in alpha 1, another point will lie in alpha 2, and so on. Now, because the alpha circles are disjoint from each other, this is really a torus inside the symmetric product. So this is a torus. And it's a torus as well. It's not really clear that for the Keeler structure these subspaces are really Lagrangian. However, turns out you can still use the same ideas as in Lagrangian Floer homology. These are totally real subspaces, and you can still count holomorphic these the same way as before and prove compactness. So great. So I guess our first attempt would be to do just this. Take this symmetric product, these two subspaces, they are clearly half-dimensional. This is 2G dimensional, these are G-dimensional. And so make alpha and beta, the alpha and beta circles to be transversal. That would show that T alpha and T beta are also transversal in the symmetric product. And I guess that could be some theory. So I guess we could look at some Floer homology of T alpha, T beta inside the symmetric product. And in fact we tried this and made some computations, and turned out that this is not a very interesting theory. So turns out in order to get something that actually a useful three-manifold invariant, you have to do something, you have to do a little bit more than this, not much. What you need to do is also fix a base point. So instead, okay, so maybe I write down this, not too interesting. Instead, fix a point, a base point, which is in the complement of all the alpha circles and all the beta circles, and this point allows us to define a codimension 2 space inside the symmetric product, which is Z cross sim_G minus 1. So here we require one of the points, at least one of the points, to be Z. And note that since Z is disjoint from the alpha and beta circles, this codimension 2 subspace is disjoint from T alpha and also disjoint from T beta. So so we define CF hat T alpha, T beta. Z is generated as an abelian group generated by the intersection points T alpha, T beta, and the boundary map of X is going to be a sum of Y in T alpha, T beta, Cxy times Y, when the Cxy, right, are integers, and they really count. So this is the count of holomorphic disks connecting X to Y, but not in the whole symmetric product, but in the complement of that subspace Vz. So that's just a small modification of what we have. Turns out that since this is a holomorphic subvariety, you can prove that holomorphic disks will have non-negative intersection with this. And turns out that the same proof that in case of Lagrangian Floer homology guarantees that d square is 0, it still works in this case. This is really a chain complex. And that turns out to be a more interesting invariant. So I guess we have a lot of work ahead of us, so we would like to see some arguments. So what we need to know, I guess, is why d squared is equal to 0. So maybe we should discuss a little bit about how to prove that. And more importantly, what we define right now is, I guess, some kind of Floer homology corresponding to T alpha, T beta, and the base point C. And strictly speaking, we also use the complex structure on sigma that induces for us the complex structure on the symmetric product, so we should be able to vary that as well. And so we have to prove that that this is really a three-manifold invariant. And turns out that there are lots of additional elaborations on this. There are more complicated versions of the Floer homology. Also, the Floer homology itself decomposes according to spin C structures and a lot of other things. So I guess the remaining 1 minute, let me give you some examples. And I guess so we have this example of alpha and beta, and it's easy to see that if you really use these two circles, then you get so a 3-manifold which is just S3. Basically, you can see that there is this torus, and you can take the solid torus, which is the inside, and the other solid torus, which is the outside. And if you really use these alpha and beta circles, you will really build up these solid torides. So, yes, that's one example. And let me just finish with a more interesting example, which is so right now, you should view this as a genus force surface, and inside we have alpha and beta circles. So let that be alpha 1, alpha 2, alpha 3, alpha 4. And for the beta circles, I will use this one, and okay. And here I can use the base point Z, and here I can use the base point Z, for example. So maybe let me put it here. Okay, so here it's easy to find the intersection of T alpha and T beta. There is just this one point. In this example, I guess the exercise would be to find T alpha and T beta, and if you're really ambitious, find the boundary map on CF hat. And show that the 3-manifold that correspond to this picture is also S3. So here we have a really easy Heegaard diagram of S3. Here we have a somewhat more complicated looking Heegaard diagram. But if you believe me on this second count, that it doesn't matter what Heegaard diagram we choose, we always get the same homology, then we should be able to see that this is true also in this case. So that's sort of an exercise to see whether we can prove it. Okay, thank you.